All right, so let's get started for today. The plan for today is to work through sections 1, 3, and 1, 4. We're running about a section or so behind schedule, but I think that's perfectly fine. We'll have plenty of opportunity to catch up as we go through the material through the course. The quote of the day today, let me make it look a little better here. The quote of the day today is from a movie called The Truman Show. This is a Jim Carrey movie, but it's not his usual, goofball comedy like Dumb and Dumber, Ace Ventura kind of movie. It's a more serious movie. Um, and the point of the show is that this guy Truman, Jim Carrey's character, has lived his entire life on a huge movie set or TV set. Um, and it's this like kind of huge dome with artificial weather and this huge town that was built. And the whole point of the TV show is people just watching him grow up. It's kind of like literal reality TV. Um, all of the people in the town are actors. There's hidden cameras everywhere. And Christoph is the like mastermind producer director guy behind this TV show. And at some point, every once in a while something will glitch or something won't work right, or um, and I think the context of this is somebody asked Christoph, like, doesn't he ever like realize that he's on a TV set? Like, how does he not realize this? And Christoph has this line. Oh, let me fix that. Christoph has this line. We accept the reality of the world with which we're presented. It's as simple as that. And I think it's a really powerful line, and I think it applies actually a lot to higher education today. And the ideas, I think, um, are related to some of the discussions about the value of higher education. So that's the quote of the day today because I think of the breadth of its application and its application in our specific field. So particularly what a lot of people are asking today is, well, for any component of higher education that's not directly related to workforce training, or basically what I'm going to be doing in my career, why should I have to do that? Why would I want to do that? Why would I want to take the time and effort or pay for this coursework? You know, if you're going to be an artist, why would you take math? If you're going to be an engineer, why would you take art history or something in the humanities? And I think most of the answers that are given are really pretty terrible answers. Even the answers given by folks in the humanities defending their own subjects, I think are usually terrible answers. One answer that I really dislike is, oh, it's like mental push-ups or something. It's like, oh, you're exercising different parts of your brain, and then you get better at that, and you can take that to your career later on. I don't think that's a great answer. There's lots of ways to exercise your brain. Why should I do it in this particular way that you're telling me that I should do it? Another answer that we hear often is they try to kind of come in the back door of workforce. Why should I take my whatever English literature, course? Oh, well, maybe if you're a salesperson, you can connect with somebody and make a sale that way if you know something about Shakespeare or whatever. Or, maybe if you're in say, well, let's say if you're an engineer and you're writing a report, and you use poor grammar, then somebody's going to look down their nose at you and you won't do as good in your job. I think those are poor answers because they don't address the fundamental question of, really why do we have general education courses? What is general education? What is the purpose of the humanities? I think the more important idea, the more foundational idea, and those might be true ideas to an extent. So I don't want to completely discard them, but I think the more foundational, the more true idea is directly related to this quote. That as we're going through, grade school, high school, we're going through our younger years, our teenage years. Um, for the most part, the reality of the world to us is maybe what we see in our family, what we see with our friends who mostly live pretty close to us geographically, what we see at school. But most of these folks have very similar realities to what we have. So the reality of the world with which we're presented is one particular reality. And in actual reality, there are lots of realities, whether that's on the other side of the world or even just a few miles away. there are people living very different realities who are equally convinced that they're being presented that reality. They accept that as the true reality. And especially in kind of today's world where things are so interconnected, uh, I think it's beneficial to see that there are other realities out there. There are other folks who have very different life experiences than yours, and to be exposed to the breadth of those possible life experiences. That's, I think, really what the humanities are about. And then when we interact with folks, we can maybe appreciate the fact that they might have a different reality than we have. They might have a different life experience than we have. They might have grown up a different way. They might have different kind of, let's say, default morals and values than we have, something along those lines. And even if we don't agree with them, maybe we can appreciate uh, the source of that disagreement and, maybe get along with folks a little bit better. Maybe that can have an impact on how we deal with folks. Again, in such an environment as today, where we have the world is becoming smaller and smaller, so to speak. So I think that's really the value of the humanities and of higher education. Now, the counterpart to that is we don't want to go so far in that direction that we neglect workforce, right? We want folks to graduate and have the skills to get family supporting jobs, to have careers, to be financially stable, things like that. But these are two things that go hand in hand. Um, but they are two separate things. The goal of the workforce side, if you're studying accounting or studying IT, like you have your courses that are preparing you for those fields, but your general education courses serve a different purpose. They can sometimes be linked, but they serve a different purpose fundamentally, which is that breadth of experience. So you want to go very deep in one field or maybe a couple fields, but you also want a breadth of experience to help you appreciate the um, the breadth of realities that actually exist in the real world and help you deal with uh, folks maybe a little differently than you would otherwise. So that's kind of my defense of the humanities. There have been, whole books written about this and so on, um, but I think that's kind of the short summarization, that we're presented with a particular worldview like Truman was. He just accepts that worldview, even when there's a bit of discord with reality. This is my worldview, but something happened that doesn't make sense with that. You just kind of push that away and stick to your worldview. And having that challenged a little bit and looking at other worldviews is an important component of higher education. And that's, I think, the role that a lot of these general education courses serve, to, look at how it feels to think in slightly different ways. Okay, so the plan for today is to go through sections 1, 3, and 1, 4, subtraction and multiplication of whole numbers. Again, keep in mind the context here is not so much to teach you how to do these operations on whole numbers, but to build kind of a strategy. We're starting by applying addition, subtraction, multiplication, division, word and application problems to whole numbers, and then we'll work up to things like fractions and decimals and so on. So let's start with subtraction. And we're going to start with modeling subtraction with the block model. And just recall that we have the idea of a block being related to the unit 1, a rod, which I'm not going to subdivide anymore, being related to the unit 10, and a square being related to the unit 100. And then we have those periods, kind of the ones period, the first 3 numbers counting from the right to the left, the thousands period, the next 3 numbers counting from the right to the left, and so on. So let's try to model the subtraction 15 minus 3. So what's the idea of subtraction? The idea is that I start with an amount, and then instead of taking another amount and kind of pushing the two together, I kind of take another amount and I, in a sense, like cancel out that amount. If we think in terms of money, 15 plus 3 is like if I have $15 in the bank account and I have an extra $3 and I go and deposit that, I now have 15 plus 3 or $18 in my bank account. 15 minus 3 is like if I have $15 in my bank account and I want to buy something for $3, I go and I remove $3 from my bank account and I give that to somebody else in exchange for goods or services. So the block model looks like I have one rod and 5 blocks. That's how much I have kind of in assets, or that's like mine, or that I start with. But then I want to take away 3 blocks. And maybe I'll actually write it this way. When I put these together, I'll kind of write it this way. And the role that these 3 red blocks, the role that the 3 blocks that are subtracted serves, is each one of them kind of like blows up, in a sense, one of the green blocks. So we have one red block, it kind of like seeks out one green block, like attaches to it. They cancel each other out. That happens 3 times, once for each of the 3 red blocks. And what I'm left with is still one rod, but now only 2 blocks. So one rod and 2 blocks, 15 minus 3 is 12. Again, just linking this back to the block model, or maybe to currency. So I could think of a block as being like a dollar bill. I could think of a rod as being like a $10 bill. And I could think of a square as being a $100 bill, right? So I could think of these in terms of the respective bills. Okay, let's continue on with the block model. I know it takes a few minutes to write some of this block model stuff out, but I think it's good to do this to get a more kind of gut feeling understanding of what's going on here. So here we want to model subtraction 34 minus 14. So I have 3 rods. I'm going to leave a little bit of a space under these rods, and then I have 4 blocks. And again, I could write my 1 rod and 4 blocks off to the side here, but I'm going to choose to write them kind of interspersed in here. And just kind of like before, whenever I see a red block, it's going to seek out a green block and cancel it out. I see that that happens 4 times. And I could do the same thing with rods. When I have a red rod, if there's a green rod, the red rod can just cancel out that whole green rod. I note that I have 2 green rods that were left over, and I have no blocks that are left over after that cancellation. So 34 minus 14 is 20. Okay, pretty straightforward so far. Let's look at one that's a little bit more complicated. It's going to start off pretty similar. So 33, I'm going to write this a little more expanded out because we're going to have to do a few extra little details here. So I have my 3 rods and 3 blocks. I'm just kind of splitting them apart a little bit so we have a little more room to work with. And then I want to take away 17. So I need to take away 1 red rod and 7 blocks. Now, if I do what I did above, I see 1 red block cancels one of the greens, another and another. But here I have kind of 4 leftover red blocks. What can I do with this? Well, what I'm actually going to do is I'm going to take one of these green rods I'm going to move it over here. And in fact, instead of keeping it as a rod, I'm going to split it into its 10 component blocks. So I need to kind of borrow one of these rods, break it up into its component blocks to make some more blocks for me to cancel out. So my one rod came over here, got split into its 10 component blocks. And now I have some more blocks that can facilitate that cancellation for these red blocks. I want to get rid of all of the red stuff. I want to make sure that all my red stuff cancels out something. And then likewise, my red rod over here will cancel this one green rod. This leaves me with one rod left over and 6 blocks left over. 33 minus 17 is 16. And again, this process was a bit more complicated. I had to kind of borrow one of the rods, split it into its 10 component parts, and then use some of those to facilitate the cancellation with the rest of the red blocks. And then I could move over and do the cancellation with the red rods and, if I needed to, red squares as well. So what if I have more than one thing being subtracted? What if I have, say, 25 minus 11? I'm taking away 11, or I have 11 red blocks. And then minus 6. Well, again, the minus 6 says that these are going to be like red blocks. These are being taken away. So I have 2 rods and 5 blocks. The minus 11 says that I have 1 red rod, 1 red block. And then the minus 6 says I have 6 more red blocks. So this is the 25 minus 11 and minus 6. Again, I'll start over here with my blocks. After I do my cancellation of all of my red blocks with all the green blocks, I'm left with still a couple red blocks. So I need to do that same process. I need to now borrow one of these green rods. It's going to kind of come over here. And I'm going to break it into its 10 component blocks. And now I have some more blocks to work with that I can use to cancel these last 2 red blocks. I've now gotten rid of all of the red blocks. I can come over and look at the rods. I have 1 red rod, 1 green rod. Those can cancel. And what am I left with? Just some of these leftover blocks. I have no rods left over. And I'm just left with 8 blocks. So 25 minus 11 minus 6 should be 8. As kind of a challenge problem or an exercise, what if I had pluses and minuses, or addition and subtraction mixed together? What if I had 25 plus 12 minus 8, plus 7 minus 11? How would I model this? So it is an exercise, maybe think through that, try to build off of the foundation we built here, with these kind of green and red blocks and try to think through how would something like this look in a block model? How would you kind of combine several elements of addition and subtraction this way using this block model? And then maybe try to find the answer. So that's just an exercise. Okay. We had some properties of addition. We had an additive identity 0. We had the commutative property of addition. The additive identity, the idea was if I add 0 to a number, I get the same number back. Commutative property of addition means that if I swap the order of addition, it doesn't matter. So 7 plus 3 and 3 plus 7 give the same result. And the associative property of addition says that if I have 3 or more things being added together, it doesn't really matter which ones I add first and which ones last. So if I had, 1 plus 2 plus 3, I can do the 2 plus 3 to get 5 and then do 1 plus 5. Or if I wanted, I could do the 1 plus 2 to get 3 and then add 3 and get 3 plus 3. And that would give the same result. So it's good to ask ourselves whether these properties that apply to addition also apply to subtraction. If they do, great, we can use them. They might be helpful to us. If they don't, we have to be very cautious and not use that in the wrong context. So the additive identity, if I have something like, say, 3 minus 0, well, if I have 3 green blocks and if I have 0 red blocks, if I have 0 red blocks, then I'm not taking anything away. 3 minus 0 is 3. Now recall with the additive identity, I had something like, 5 plus 0 equals 0 plus 5 equals 5. So if I put the 0 second, I got the same answer. The commutative property of addition said that if I flip the order and put the 0 first, I still get the same answer. Is that the case here? If I try to do something like 0 minus 3, I'm not really sure how to model that or how to make that work out because I have 0 green blocks and 3 red blocks. I don't have any green blocks to cancel. So 0 minus 3 looks like, let's just say like an empty green box space. And 3 red blocks, like these 3 red blocks are looking for something to cancel with, and I don't have anything for them to cancel with. So I think the identity 0 works the same way if I'm subtracting it. If I have number minus 0, I get the same number back. But if I have 0 minus number, that seems to be a completely different idea. It's not an idea that we can't handle at all in mathematics. It's an idea that we just haven't run into yet. So I do have to be a little bit careful. The additive identity 0 works in a similar manner with subtraction, but only when 0 is the thing being subtracted, not when it's the thing first that we're subtracting something from. Now, if we had a similar commutative property, if we had a similar property to addition where if I flip the order, I get the same answer, well, then I shouldn't have this discrepancy that I saw in the identity. In other words, 3 minus 0 should be the same as 0 minus 3. Clearly, that's not the case. So clearly, this does not apply to subtraction. In other words, 5 minus 2 is not the same as 2 minus 5. Right? Having $5 in your bank account and withdrawing $2 leaves you with $3. If you have $2 in your bank account and you try to withdraw $5, the teller is going to say you don't have enough. Those aren't the same operation. They aren't the same result. If we did it for addition, if I have $5 in my bank account and I go to the teller and put $2 more in, I have 7 in my bank account. And vice versa. If I had $2 in the bank account and I put 5 more in, I have $7 in the bank account. Same result there. So for addition, it works, but for subtraction, not so much. Right? We've broken that symmetry because instead of having like all green blocks and just some green blocks over here, some over here, and we're smushing them together, now some of the blocks are colored green, some red. They have different roles. The green ones are kind of already in existence, and the red ones, their job is to kind of blow up the green ones. They have different roles. There's no longer a symmetry between the two. That breaking of that symmetry in their roles means that this commutative property, the ability to switch their roles around, does not apply to subtraction. So this is important. In subtraction, we have to be very careful about which number comes before the minus sign, which number comes after. In addition, we can switch them around more freely. The associative property of addition, does it apply to subtraction? This is a little bit more of an advanced concept. This might be pushing a little bit further into some future material. But because, again, I know that everybody has had exposure to this before, I just want to point this out. So if you don't fully grasp this, or if you say, hey, we haven't completely gotten to that material yet, that's perfectly okay. But I think it's good to just kind of lump these together in one discussion of the different properties. So if I consider something like, let's say 8 minus 2 minus 3, is the order that I do these important? In other words, if I did, oh wait, let me reverse here. 8 minus 3 minus 2 is what I wanted to write down. If I did this operation first, 8 minus 3 is 5. And then I did the minus 2, 5 minus 2 is 3. But what if I did it the other way around? What if I did the 3 minus 2 first? 3 minus 2 is 1. And if I did 8 minus that, 8 minus 1 is 7. I see that I don't get the same answer. So this associative property of addition, at least at kind of a first passing glance, doesn't really apply to subtraction. Now, it kind of turns out that we can force the issue. We can kind of force subtraction into this mode of addition and use some of these things like associative property and commutative property. But that really takes it really follows from a larger discussion. So that's, but at first glance, these first principles, this associative property also does not apply to subtraction. So these don't readily apply in the same way that they apply to addition. We can kind of, in a sense, force them to apply to subtraction by making subtraction look like addition. But again, that's a slightly more advanced concept. So we're not going to handle that here. We're just going to say, at least at kind of a first glance, at a first pass, neither the commutative nor the associative properties that do apply to addition, they don't really work for subtraction, at least not, not as simply as they do for addition. And the additive identity has, on one hand, a similar property that if the 0 is subtracted from a number, it leaves the number intact. If there are 0 red blocks looking to blow up green blocks, then we just keep all of our green blocks. But if I try to do it the other way, if the 0 is the first number minus something else, then I have red blocks in search of green blocks, and there's no green blocks to be had. So I don't really know what to do with that, at least not yet. So these properties, we have to be very careful. They apply to addition, but they don't apply nearly as easily to subtraction. Okay, so what if we want to subtract whole numbers without the block model? What's our strategy? Well, we started off kind of similar to how we started with addition without the block model. We line the numbers up above one another so that their place values are all nicely lined up. We subtract the digits in each place, and we work from the right to the left. We start by canceling out the blocks, and then the rods, and then the squares, and so on. So if we look at something like 23 minus 10, again, very important that I get these in the correct order. I'm going to put the first number on top, the second number on the bottom, and then I start with basically I have 3 green blocks. I have 0 red blocks. I maintain my 3 green blocks. 3 minus 0 is 3. I have 2 green rods. I have 1 red rod. 1 red rod cancels one of the green rods and leaves me with 1 green rod left over. 2 minus 1 is 1. There's 1 rod left over. So 23 minus 10 is 13. Similarly, I have 84 minus 63. Again, I'm careful that when I write these, I line up my ones digits, my tens digits, and so on. 4 minus 3 is 1. 8 minus 6 is 2. And there's my answer. So I can do subtraction of bigger numbers by just doing kind of subtraction coming down each of the columns, right? I cancel out my blocks first. I cancel out my rods second. I cancel out my squares third. I move up a period. I do the same process. So what about 790 minus 525? Again, I'm careful to line up my ones, my tens, my hundreds places. But here I have a bit of a problem, right? I have 0 green blocks to start with, and I have 5 red blocks. Those red blocks need to be taken care of first. I need to have something for them to match with, but I don't have anything right away. Well, what would I do? I would grab a rod, bring it over, split it into 10 blocks, use some of those green blocks from the rod to get rid of the red blocks, and then we'd have some of the green blocks from the rod left over. So we subtract the digits in each place value, but if the digit on top is less than the digit below, in other words, like 0 is less than 5, so I don't have enough green blocks to satisfy all of the red blocks, well, then I borrow. That's what we call it in this kind of abstract sense. We call it borrowing from the next place. I, grab a rod, bring it over to the block side and split it into its 10 component blocks. I borrowed a rod to move to the block side and allow some cancellation of these blocks. So instead of thinking of this 790 as 7 squares, 9 rods, and 0 blocks, I'm going to choose to think of it as 7 squares, 8 rods, and 10 blocks. Or maybe I'll actually write that in even a different color. So I have 8 rods left over because I pulled one of the rods over to the block side. And then I have 10 blocks. I typically just kind of slide that one there in front of whatever number we started with. So that 8 rods are left over. The 1 rod that I brought over split apart into 10 blocks. And now I do 10 minus 5. Well, that's 5. I now have 10 blocks, 10 green blocks, 5 red blocks. 5 of the green blocks go to cancel the 5 red blocks, and then I have 5 green blocks left over. Now I borrowed one of the rods. I pulled one of the rods over to the one side to facilitate that cancellation of the red blocks. I have 8 rods left over. I have 2 red rods. 2 of those cancel. 8 minus 2 is 6. And then for squares, I have 7 green squares, 5 red squares. 7 minus 5 is 2 squares left over. So that's the idea of borrowing. I either borrow a rod, move it to the block side, and split it into its 10 component blocks, or maybe I would borrow a square, move it to the rod side, and split it into its 10 component rods. So if we think of, say, 493 minus 390, here I can actually, I think it's actually quicker to think of the rods and blocks model. Oh, how did I get the 8? Yeah, so up here I had 7 squares, 9 rods, 0 blocks. And the problem is, and those were the green ones. The problem is I have 5 red blocks and they have 0 green blocks to cancel with, right? Um, I have whatever's going on over here plus 0 blocks, 0 green blocks, and I have 5 red blocks. They don't have any green blocks to cancel with. So then what I have to do is I have to look at where can I get more blocks from? Well, let me just write these as S. I have 7 squares. They're not going to come into play right now. And then I had 8 rods. Or sorry, I started with 9 rods. I also have 2 red rods and I have 5 red squares. I'm just drawing the squares as S so I can draw them a little faster. I want to start by canceling out my blocks, but I don't have any green blocks to cancel with. I have red blocks that are in search of green blocks. So what I'm going to do is I'm going to take one of my rods, come over here, I'm going to split that rod that's 10 blocks into its component blocks. And now I have blocks that my red blocks can cancel against, leaving me with 5 blocks. However, I now only have 8 rods left over because I started with 9 and I pulled one of them over to the block side. So the 9 turned into an 8, and then I kind of shimmied the 1 in there next to the 0. So instead of 9 rods and 0 blocks, I have 8 rods and 10 blocks. It just helped me to think about one of those rods as its 10 component blocks to facilitate the subtraction. Now, there are some times like this one where even, subtracting without the block model, so to speak, it's even a little quicker to think of the block model. If I have 93 minus 90 and 400 minus 300, I can think of this as like 4 blocks or 4 squares and 93 blocks minus 3 squares and 90 blocks. I know that this is just going to give me 3 blocks left over, 1 square left over, and 0 rods. So there are times that, it's quicker to kind of think of this blocks and rods model, but I could still do this. I could still do this in this format with no problem. 3 blocks minus 0 blocks is 3. 9 rods minus 9 rods. All of my rods get canceled out. I have 9 green rods, 9 red rods. They all go away. And 4 squares minus 3 squares is 1 square. Either way I do it is fine. But sometimes it's a little bit quicker if I realize, like this one here, that I could split this into 4 squares and 93 blocks, minus 3 squares and 90 blocks. 4 squares minus 3 squares is 1 square. 93 blocks minus 90 blocks is 3 blocks. I might realize that pretty quickly. But if I didn't, I can always just revert to the general strategy. Okay, then let's look at 8153, 8,153 minus 3978, 3,978. So here again, I have, say, 3 green blocks and 8 red blocks. I don't have enough green blocks to cancel all of the red blocks. I need to take a rod. So instead of having 5 rods, I'll have 4 rods. I need to move 1 rod over to the block side, break it into its component blocks, giving me 10 more blocks. So we'll write that as like a little 1 next to the 3 there. So now we have 13 green blocks and 8 red blocks. 13 minus 8 is 5. After all my red blocks match up and destroy their green blocks, I have 5 green blocks left over. Now here I want to do my rods next. I have 4 green rods and unfortunately 7 red rods. I don't have enough green rods to facilitate the cancellation of all 7 of the red rods. What do I need to do here? Well, I do have 1 square that I can work with. Well, if I take that 1 square, move it over to the rods side, I have 0 squares left over. And let me kind of write this in a parentheses like that so it looks a little cleaner. I have 0 squares left over, and then I break it into its 10 rods. I had 4 to start with, and I got 10 more rods. I now have 14 rods to facilitate the cancellation of the rods. 14 green rods, 7 red rods. 14 minus 7 is 7. I have 7 green rods left over. And then once again, I have 9 red squares. I have 0 green squares. I can't cancel any of these red squares. I got 9 of them I need to cancel. I borrow a block from the next period, kind of a super block. I'm left with 1 fewer block in that next period, but that kind of super block can break into 10 squares of the previous period. I have 10 squares now, 10 green squares and 9 red squares. I can do 10 minus 9. That cancellation yields a 1. So I have 1 green square left over after all that cancellation. And then lastly, moving on to my next period, onto the thousands period, I have kind of 7 blocks from the thousands period, 7 like super blocks that are green, 3 of those blocks that are red. 7 minus 3 is 4. Maybe I'll put the comma back in just to make it easier to read. And my result is 4,175. So you see that subtraction can be pretty nice and simple. It can be a little bit complicated if we have to borrow once, or sometimes we have to borrow a couple times and it can be even more complicated. Okay, give me just a second here. Sorry, I don't want to sneeze right into the microphone and blow out all your eardrums. Are there any questions on anything so far? Okay. So we looked at some words indicating addition, things like plus or total, things like that. What are some words indicating subtraction? If you see these words, you might be led to think subtraction. Well, words like minus, difference, what's the difference between these two things? Decreased by, less than. We have to be a little bit careful with less than because sometimes it indicates subtraction and sometimes it indicates relative size. Like we might say that the number 3 is less than the number 8, right? So we have to be a little bit careful with that one. Subtracted from is a pretty clear one. These aren't super common terms, but in addition, we had addends in their sum. So if I take addend plus addend equals sum, well, for subtraction, we have minuend. Those are kind of the green items, so to speak, minus subtrahend. And that's equal to the difference. Yeah, now that I have two screens, my trackpad is like split in half kind of, so I have to get used to writing again. So my writing is sloppier than usual, which is not a high standard to start with, unfortunately. Um, but yeah, so again, these aren't super common terms, but just in case you see them, minuend minus subtrahend equals the difference. I wouldn't like study this for an exam or something, but you might remember those terms now. Okay, so let's look at some applications of subtraction. So first example, John wants to buy a laptop that costs $840. He has $685 in his savings account. How much more does he need to save in order to buy the laptop? Well, so John has 685. If he saved more money, say if he put another $5 in a savings account, he would have what, 690. That's getting closer. I could keep doing trial and error like this. If he saved $100 more, well, that would be 785. That's getting closer. If he saved $200 more, that's $885. That's overshot it, right? I guess I could keep doing trial and error like this, getting closer and closer to how much I need to save. That's going to be quite a time consuming process though, right? I know it's more than 100, it's less than 200. Let's try 150. Does that work? I either overshot or undershot, and then I can adjust from. I think we can see it's going to take a while to zero in on the result. How else could I think about this? Well, so I want to have $840 and I currently have 685. So kind of my goal is 840 and I've achieved this much of my goal. Right? My goal is to have, say, 840 or 8 squares. Let me just write them this way. 8 squares, 4 rods, and 0 blocks. Now I've currently achieved 6 squares, 8 rods. Let me just write them as R. And 5 blocks. Right. So my goal is to have $840. I've satisfied 685 of that. I can kind of cancel out 685 units of that goal that I've already achieved. How much do I need still to still achieve? Well, I see that this is really just a subtraction problem. 840 minus 685. This is a much better way to approach this problem than thinking of like 685 plus what number gives me 840. I'm going to have to try a whole bunch of different numbers before I hit on the right one. But here, 840 minus 685, I can do this subtraction now. Again, I have 5 red blocks. They don't have any green blocks to cancel with. I need to borrow a rod. I'll borrow one of the 4 rods and turn it into 10 blocks. So I've taken, say, this rod. I've made 10 blocks from it. That gives me some blocks for the red ones to cancel. 10 blocks minus 5 blocks. 10 minus 5 gives me 5. Now I have 3 green rods and 8 red rods. I don't have enough green rods to satisfy the cancellation required from those 8 red rods. So from the 8 squares, I borrow 1, leaving me with 7 squares left over. So I've borrowed one of these to make 10 more rods, 10 more green rods. And now instead of 3 green rods, that looks like a B kind of, instead of 3 green rods, I now have 13 green rods. Those 13 green rods, while 8 of the red rods cancel out, 13 minus 8 is 5. And then 7 squares minus 6 squares, that works just fine. 7 squares minus 6 squares leaves me with just 1 square. So John needs to still save $155 to get this laptop. And we get that answer by subtraction. Could we have found it by trial and error with addition? I guess so, but it would have taken quite a while, right? Much easier and much more elegant to solve it with subtraction. All right, another example. So some courses are points based for their grading criteria. Ours is percent based, but you can always kind of just convert from one to the other if you want to. But here, Sarah needs 350 points to pass her course. So let's say these first 4 tests, she scored 75 points, 50, 70, and 80 points. How many more points does she need to pass the course? So this is a similar question to the John's laptop question. Her goal is 350 points. And how much of that has she achieved? How much of that has she kind of chomped away at from these first 4 tests? So how much is done? 75, 50, 70, and 80. So she needs 3 squares, 5 rods, 0 blocks. That's kind of the green. And then she's kind of gotten rid of the need for 7 rods and 5 blocks. Gotten rid of the need for 5 rods, gotten rid of the need for 7 and 8 rods. Or again, we can phrase this in terms of a subtraction problem. She needs 350 points. She's already achieved 75 from the first test. So she doesn't need those points anymore. She's already achieved 50, 70, and 80 from the other tests. So we have this repeated subtraction. Now we can, I guess, do these one at a time. 350 minus 75, get that answer. Take that answer, minus 50, get that answer, and so on. There's nothing inherently wrong with that, but it's kind of a laborious process. It might even be an error-prone process because we might kind of forget where we're at in this long process. We could do it. It's not a problem, right? We could do 350 minus 75, which would give us 275, and then subtract 50 from that. That would give us 225, subtract 70, and so on. But again, that's pretty laborious and error-prone. So what could I do? I could take kind of a shortcut here. And as an aside, if you're not comfortable with this shortcut, you can do it that way. There's nothing wrong with doing it that way. Just be really careful that you know exactly what steps you've done already and what you need to do. So it might be good to write something like, I did 350 minus 75. That's 275 minus 50 minus 70 minus 80. And then I can do 275 minus 50. That'll end up giving me 225 minus 70 minus 80. So as long as I'm very careful with kind of the note taking and the bookkeeping and keeping everything straight, again, not a bad way to do it this way. But could I do it a slightly different way that might be a little clearer? Can I do it all kind of in one step? So I have 350. Those are my green, like my assets, so to speak, the green things that I have floating around. And then I have minus 75, minus 50, minus 70, and minus 80. I've been careful to line up all of my ones places, all of my tens places, and so on. And here I might start by thinking, okay, I see that I need at least 5 green blocks to cancel those 5 red blocks. I don't have any green blocks to start with, so let me borrow a rod. And I didn't quite leave myself enough room to shimmy a 1 in there. Let me just move this over just a smidge. So I borrow a rod from the 5 rods. That leaves me with 4 rods left over. I move it to the blocks. I break it into 10 blocks. Now I have 10 green blocks. And these 5 red blocks are going to cancel with 5 of those. So 10 minus 5 is 5. Now 7, 5, 7, and 8, those are all rods that I need to get rid of. So how can I handle this? Well, if I, let's say, take 1 square, convert it into 10 rods, and I go piece by piece. 14 minus 7 is 7. So those first 7 red rods cancel 7 of the green rods and leave me with 7 green rods left over. Minus 5, 7 minus 5 is 2. I don't have enough green rods, just 2 left over to cancel the next 7. Okay, so I need more rods because I have more terms that I'm subtracting off. It turned out that I need to borrow another square. Maybe I need to borrow 2 squares. So instead of having 3 squares, I borrow 2, split those into 10 rods each. That gives me 20 rods contributed to the rod side, but I only have 1 square left over. Well, 24, it's getting a little difficult now with keeping all this straight. 24 minus 7. So we can count on our fingers or whatever, but 24 rods minus 7 rods is 17. If I take away another 5, 17 minus 5 is 12. If I take away another 7, 12 minus 7 is 5. But now I have 5 green rods. I need to take away 8. I don't have enough. I actually need to go back again. I need to borrow all 3 squares, turn them into 30 rods. And now the subtraction is getting challenging, right? I might even need to come off to the side. This is something that we often do in math, right? Come off to the side and do some scratch work to help me with this. 34 minus 7. Well, 3 rods and 4 blocks minus 7 blocks. That's 2 rods and 14 blocks. 14 minus 7 is 7. So 34 minus 7 is 27. And that takes care of that one. 27 minus 5. 7 minus 5 is 2. And the 2 minus 0 is 2. 22 minus 7. I borrow 1. 12 minus 7 is 5. 1 minus 0 is 1. 22 minus 7 is 15. And 15 minus 8 is 7. So I could do it this way as well. So I have a couple of different ways I could do it. Can anybody think, I mean, both of these ways seem pretty complicated and like it would be really easy to make a mistake in either of these ways, right? Can anybody think of a simpler way that I could do this? Is there something I could do on the front end? Something that I could do to simplify the process if I do a little bit of work on the front end that will make my subtraction a whole lot easier?
You could add what she already has.
Yeah, exactly. So by being a little bit creative, we can say, wait, well, maybe instead of thinking of it this way, we could do that. This is the kind of just, follow your nose way of doing it, but it's really complicated. Again, if I think of the blocks model, I can think that I have like 7 rods and 5 blocks that are all red ones. I have 5 red rods. I have 7 red rods. And 8 red rods. Well, these are all the same type, right? These are all red squares, blocks, or rods. If I just want to know what's the total red squares, blocks, rods, I could just squish together all of the red ones. Well, that's just addition, right? Or in other words, I could figure out the total of these.
275.
I could sum just the red ones, just the 75, 50, 70, and 80, get a number from there, and then do a much simpler subtraction. So a lot of times if we follow our nose and just take kind of the simplest path forward, maybe that doesn't turn out to be the best. If we plan and think a couple of steps ahead and say, man, subtracting off all of these numbers one after the other, that's going to be kind of a big mess. It's going to be easy for me to get lost. I could do it. I could make it work. But if I do a little bit of work on the front end, if I strategize a little bit and say, okay, let's just figure out how much red stuff we have overall. I want to do 75 plus 50 plus 70 plus 80. I'm going to do an addition problem here to help me with my subtraction problem. So I see that I have 5 blocks, 7 and 7 is 14, 14 and 8 is 22, 22 and 5 is 27. I actually have, instead of all of this, I can just think of having 275, 2 squares, 7 rods, 5 blocks. And now I can do an easier subtraction. 350 minus 275. I just kind of aggregate all of the green stuff. I mean, here there was just one green thing, 350. And then I aggregate all of the red stuff that's being subtracted off by adding together all of the things being subtracted. It's a little bit counterintuitive. Why are we adding together things being subtracted? Well, because we're keeping them as red items. So we're adding together all of the red things. So we have 275 red items. And now I go through my same process as before. I borrow 1 from the 5. My 1 rod turns into 10 blocks, leaving me with 4 rods left over. 10 minus 5 is 5. I have 4 rods. I need to get rid of 7. I borrow 1 square, break it into 10 rods. This gives me 14 total rods, minus 7 is 7. And 2 squares minus 2 squares is 0 squares, or I'll just not write that 0. Even though I had to do 2 problems, each of the 2 problems was much more straightforward. So a lot of times if I see a problem like this that has a lot going on, it really is beneficial for me to take a step back and say, okay, this looks like a complicated problem. Is there something else that I can do? Is there a way that I can simplify it? Is there a little bit of calculation I can do on the front end that will make the remaining calculations easier? That's another really good strategy. It's, it's one of those things that I think comes with experience when you say, okay, this is a problem that's complicated enough that I'm going to look for simplifications, or this is a problem that's simple enough, I'm not going to worry about simplifying first. So it's a little bit of an experience thing, but I think we could see that it, no matter how we approach this initially, if we just started trying to answer the problem right away, um, we could see pretty quickly that it was going to become very complicated. And at that point, maybe it's good to rewind a little bit and say, okay, I went a little bit down this path. Maybe that's the only path to go down. Maybe it's just a complicated problem. But maybe if I back up a little bit, I can seek out a different path that is a little bit easier. Any questions on this? Okay. So moving on to section 1.4, multiplication, multiplying whole numbers. So we could look at, say, pictures like this. I mean, the ones I could find on the internet were all animals, but you could imagine whatever you want here. So if I wanted to count these groups, how many animals are there in this picture? I could go, 1, 2, 3, 4, 5, 6, 7, 8, 9. I could count each one and see that there are 9. That's, I guess, not too bad when there are only 9 of them, but if there were a whole bunch, if there were, 42 of them, that might be kind of cumbersome. The other thing that I might notice is that there's an order here. There's a structure here that I can leverage. In other words, I know that in this row, there's 1, 2, 3. And in fact, I know that each of the rows has 3. I could choose to get to instead recognize that I have a row of 3, a second, and a third row of 3. I have 3 plus 3 plus 3 is 9. 3 plus 3 is 6. 3 more is 9. But I actually noticed that each row consists of 3 B's in this case. But I also have, let's say, row 1, row 2, and row 3. I actually have 3 rows, each of which has the same number of B's. So by putting them in this orderly fashion, I see that I have 3 lots of 3. When I do repeated addition like this, when I'm adding the same number to itself over and over, that's what I call multiplication. So because I'm adding the number 3 to itself 3 times, I represent that as a multiplication 3 times 3. This multiplication 3 times 3 ends up being equal to 9. Or similarly, if I have these frogs down here, I have 5 in each row. And I see that I have 2 rows, row 1 and row 2. I'm adding 5 to itself 2 times. I see that that's just 5 plus 5 or 10. 2 times 5 is 10. So what is multiplication? It's simply repeated addition. It's simply, so 2 times 5 means add 5 to itself 2 times. And when I say add 5 to itself, I mean count the first as well. So I take 5, I add another 5, that's 2 times 5. Or add 3 to itself, how many times? 3 times. 1, 2, 3. So I can think of multiplication in kind of this grid or array model, ARRAY, as it's sometimes called, or it's really just repeated addition. Is there a question? All right. Okay, so we have at this point one word indicating multiplication, the word times. Or we might say, multiplied by or something like that. We do, however, have several symbols for multiplication. Before, for addition or subtraction, we had one symbol for each of those. For multiplication, we have this kind of times sign. 3x 5, 3 times 5. We can also indicate multiplication simply with a dot. Or we can indicate multiplication by just putting one number kind of right next to another number that's in parentheses. So like 3 parentheses 5 means 3 times 5. So we kind of roughly think of this as like omitting the operation. If we omit the explicit reference to the operation, that almost always means multiply. So when you see two different mathematical entities that are like right next to one another, and there's no explicit operation, there's not a plus, minus, times, or divided by or something between them, the implication is almost always multiply. The one exception to that is something like mixed numbers, where you might have like 2 and 1/3. Unfortunately, the operation here is plus. That's a very special case, though. When we multiply, we have factors that we multiply together, and they make a product. So factor times factor equals a product. So up here, 2 and 5 are factors, and 10 is their product. If we multiply, say, 4 by 5, 4 times 5, using the box model, I have, let's say, 4 rows of 5 each. To split this into kind of 5 columns, I use 4 internal lines. Be a little careful with that. If I want to split into 5 columns, I use 4 lines to do that, right? I do 4 cuts to make 5 different things, because I kind of started out with one thing. One cut makes 2 things, 2 cuts makes 3 things. And then if I want 4 rows, I put 3 horizontal lines. So just be a little bit careful with the number of lines that you draw. I can see that I have 4 lots of 5, 4 groups of 5, or this gives me 20 individual squares that I can go through and count if I want to. Or this gives me 5 plus 5 plus 5 plus 5 is 20. So we could use this box or array or grid model to model multiplication. So an important, say very important thing in multiplication is this idea of the times tables. So this is what the times table looks like. For instance, it's saying that if I wanted to do 3 times 4, I can locate, say, the row with the index 3, the column with the index 4, and I look in the table and I see a result of 12. So this first column represents one of the 2 factors. This first row represents another of 2 factors. And their product is in kind of the field of the table, the kind of bottom right part of the table. We haven't discussed this yet, but multiplication is commutative. So it doesn't matter which index you use for which factor. 3 times 4 is the same as 4 times 3. We see that we get the same answer of 12. Right? If I have 3 rows of 4 or 4 rows of 3, or if I have, 2 rows of 5 or 5 rows of 2, if I kind of tilted this 90 degrees, I get the same number. So it doesn't matter when I'm using a times table. whether if I have 3 times 4, whether I take the 3 from the top row and the 4 from the left column, or the 3 from the left column and the 4 from the top row, doesn't matter. I just need to make sure that I get 1 3 and 1 4, not like 2 3s or 2 4s or something like that. So this is such an important idea that I would say that it's worth it to practice it every day until you feel very comfortable with it. So actually the language app Duolingo, they actually have like a language that's math, and it's kind of gamified. It's kind of fun to do. So it's not a bad thing to go through. You can sign up for Duolingo for free. You can kind of go through this math, language kind of thing. It's not a language really, um, but you can go through the practice problems on there and do a couple of those sessions each day. Maybe you know, do 2 lessons in the morning, 2 lessons in the evening or something. They only take a couple minutes each, but that just helps you drill some of these basic math facts. And, I know that you can figure out what 3 times 4 is, but knowing it off the tip of your tongue is much more beneficial. You can use at the end of our section in the textbook, there are some partially filled in times tables. You can use those as examples and kind of go through and complete them. You can also make flashcards, so taking, say, index cards, or just take, sheets of loose leaf paper and cut them up into a bunch of smaller pieces. And on one side, you write, for instance, something like 3 times 4. And on the back side, you would write 12. And you look at this side, you'd say 3 times 4, what is that? 12, you flip it over and check your answer. You can use this table to write those out. And it's a good idea to know the times tables from 0 up to 9 so it's a good idea to know this whole table. I know that seems like a lot of work, but it's one of those things that if you spend 5 minutes a day, maybe in the morning, 5 minutes in the evening, and you do it each day, every day, and drill it throughout the course, you'll be surprised how quickly you work your way towards knowing all of these just off by heart. Okay, so what are some properties of multiplication? When we had this idea of 0, the additive identity, that if we add 0 to a number, it leaves the number unchanged. What is the 0 property of multiplication?
0.
If I multiply any number by 0, whether that other number is 0 or 1 or 8 or 9, I see that my result is always 0. Right? In other words, if I'm thinking of like groups of 5 frogs, if I had 2 such groups, I would have 10 frogs. If I had 1 such group, I would have 5 frogs. If I had no such groups, if I had no groups of 5 frogs, I have no frogs. And it doesn't matter how big the number is. It could be a million times 0, still 0. Any number multiplied by 0 gives me the result of 0. This is interesting, right? Who would have thought that 0 being such an important thing for addition it also has this really important property for multiplication. So the identity property for addition says that if I add 0 to any number, I get the number back. The 0 property for multiplication says if I multiply any number by 0, I get 0 back. Not the original number, but I get the 0 back. So what's the multiplicative identity? What's the number that I can multiply any other number by and get the other number back rather than itself? That's the number 1. Right? 4 times 1 equals not 1, but 4. 10 times 1 equals 10, and so on. So if I multiply by 0, I get 0 back. If I multiply by 1, I get the original number back. Multiplication is commutative, as we can see from this table. For instance, 4 times 3 equals 3 times 4. And that always works. Whatever two numbers you pick, if you switch their order and multiply them, you'll get the same answer. Does the associative property of multiplication work? Yeah, it does. 4 times 3 times 2, if I do the 3 times 2 first, I get 4 times 6. What is 4 times 6?
24.
Exactly, 24. 4 times 6, 24. Or if I do the 4 times 3 first, same thing. If I have multiple numbers multiplied together, I can multiply them in whatever order I want. One kind of side note is it's much easier to multiply by 10 than it is to multiply by other numbers. So if I have like 3 times 5 times 2, I probably don't want to start with the 3 times 5 first. I want to start with the 5 times 2 first because that makes a 10, and 10s are easy to multiply by. 3 times 10 is just 30. So that's kind of a side note. We'll see a little more about that next time. Okay, so the next big topic is multiplying whole numbers without using the block model. I think since we only have 6 minutes left, and this is kind of starting a whole other discussion, I think we'll end it here for today. And when we come back next time, we'll look at multiplying whole numbers without the block model. We will look at a couple of application problems, and then we'll move on to division of whole numbers. So we're running a little bit behind schedule, but especially for this foundational material, I think it's okay for us to run a little bit behind to make sure we have this material covered well. Let me stop the recording.